Okay, so let me just draw a quick graph of this. Now, we actually know what s of t equals t squared should look like. That's just a normal quadratic. And it's the one that we're most used to. So s of 0 is 0. Right? After 4 seconds, he's moved his way up to 16. And in this case, 4, 16, like that. This would be a parabola. If we could talk about negative time, where was he 4 seconds ago? Well, he was actually at 16 as well. He made his way back to 0 at negative 4 seconds. So 4 seconds before we started, this guy was actually heading back to the starting line. And now he's heading back to the starting line. And now he's moving back up to 16. And now he's going to continue his path in the next 4 seconds. He will be 2, 3, 4. He will be at 64. So this parabola there we go. And we're saying, on average, what is the rate of change from 4 seconds to 8 seconds? So if I draw a straight line through there, instead of a curve, this straight line the slope of this straight line represents the average rate of change from this point to this point. Let's call this P and this Q. So what is the average rate of change? Well, we figured out the average rate of change is simply delta y over delta x. Here we have 8, 64. Here we have 4, 16. Delta y over delta x is 64 minus 16 over 8 minus 4, which equals 48 over 4 and equals 12. The slope of this line is 12. Now let's check that out. How far did I go this way? I went 4. How far did I go up? I went 48. On average, each one step is going up 12, another 12, another 12, and another 12. So sure enough, for every 1 second, it's going up 12 on average, right? We know that this quadratic doesn't actually follow a straight line, so it actually goes a little bit slower here, and it speeds up there for an average of 12. For fun, let's do from 0 to 8 seconds. Well, from 0 to 8 seconds, we can actually draw our new P is here. Get rid of you, P. Let's use a different colored marker here. Alright, so new P is at 0. Our Q will be at 864, 0, 0. And simply, our velocity in this case is 64 minus 0 over 8 minus 0. And that is just 64 over 8, which equals 8. Okay, so on average, from 0 to 8, he's only going 12 meters per second. Or sorry, 8 meters per second. And that makes sense because we see that at the beginning he's actually much slower for the first 4 seconds, and then he speeds up. So the last 4 seconds on average is going to be higher than the total because this is the slowest part of his trek. Now, what you would notice here is that the velocity, the average rate of change of velocity is actually, or sorry, the average rate of change of the position is actually your velocity, right? The average rate of change from 0 to 8 seconds of where he is, so first he's at 0, then he's at 16, then he's at 64, and the place where he is has a slope of 8. But if you look at it, if I went from 0 to 64 in 8 seconds, how fast was I going? What was my velocity? My velocity was actually 8 for every second, 8 meters per second. So we're seeing that the velocity is actually the slope of the average velocity is the slope of the position function. Interestingly enough, which we'll look at in a couple chapters, but the acceleration would be the slope of the velocity function. So if I were to draw the velocity function, and take the slope at any point, that would actually show you the average acceleration for that part. Okay? What if we wanted to know the exact velocity at any one point? How fast is he moving at exactly 4? When he is here at 16, it's at 4 seconds. How fast is this guy moving? Well, this is where we are going to use the skills that we learned in last section. And we're going to say, what we would have done in the past is we would have taken the tangent again and found the slope of the tangent between, let's say, 4t equals 4 and maybe t equals 4.0000001. And we would say, you know what, I'm sure this is close enough. We all agree that this is what the velocity is at that exact point. But now I'm going to use the skills that we've just learned. And so the velocity at 4 seconds is actually equal to, so it's going to be delta y over delta x again. Velocity is going to be, we're going to do the limit as h approaches 0 of s of 4 plus a little bit, right, plus h, and we're going to get h as small as we possibly can. We're going to actually get it right down close to 0, minus s of 4 all over h. Now what did I say? I said s of 4 plus h is where this thing is when it's just a little bit after 4 seconds, right? And we know it's headed this way. It's going to be like 16 point something, very, very small. S of 4 is actually 16. We know that. After 4 seconds, he's at 16. So this is actually our delta y. How high was he after 4 seconds? He's at 16. After 4 and a little bit, he's just a tiny bit higher than that. So this is your delta y. Your delta x is how much time did we allow before we measured that next height, and that's h, right? And that h is going to be a very, very small amount, right? The smaller the better, right? And let's just go through this very quickly. This is equal to the limit as h approaches 0 of, we know that s of t equals t squared, so s of h, or s of p is p squared, s of happy face is happy face squared, and s of 4 plus h is 4 plus h squared. So 4 plus h squared minus s of 4, which is 4 squared, all over h, equals the limit as h approaches 0. Now I'm going to go through this a little bit quicker than you might like. This is going to be 16 plus 8h plus h squared minus 16 all over h. Let's say that I don't need this anymore. So we can say that limit as h approaches 0, 16 minus 16, these guys cancel. Goodbye. We have, and I'm going to take out an h from what's left, because we know that we always end up doing that anyways. 8 plus h times h. So this is 8h plus h squared all over h. These guys cancel just like we knew they would. Equals the limit as h approaches 0 of 8 plus h. And at this point, I have no problem plugging in h is 0. It's not going to give me 0 over 0. So I can just say that this is 8 plus 0, which is straight up 8. So at exactly 4 seconds, the instantaneous rate of change, or velocity, is at 4 seconds is actually 8 meters per second, if those are indeed your units. So we now know average rate of change is simply, let me erase this, the average rate of change between, let's say, 4 seconds and 8 seconds is going to be s of 8 minus s of 4 over 8 minus 4, delta y over delta x. And the instantaneous rate of change is going to be the limit, let's say at 4 seconds, is going to be the limit as h approaches 0 of s of 4 plus h minus s of 4 all over h. Okay, so this one, we need to take the limit, let me actually write this as v of 4. The limit, because we want the instantaneous rate of change. And this one here is average velocity. And in brackets, I'm going to say from 4 to 8 seconds, basically. Okay, I didn't put the units, but I'm just talking seconds. It could be hours, who knows. So in general, the average velocity is equal to s of b minus s of a over, let's say that b and a are two spots that we've chosen and we want the average between them, over b minus a, whereas the instantaneous velocity actually equals the limit as h approaches 0 of s of a plus h. So I'm not saying exactly where, I'm saying anywhere you want, plus h. Now we're going to make that h really small. We're actually going to make it approach 0, minus s of a all over h.